Do you want to talk about a four-color theorem a bit and computer proofs? Is that something you've got opinions on? And
yes,
maybe even the Kepler sphere packing conjecture. You were involved with a proof of that.
the four-color theorem was the first time that such discussions arose.
Although we'd run into it in group theory.
Haken and Appel, I almost spoonerized those two names, proved it jointly.
So they reduced the proof to an enormous calculation, which they did by machine.
They interacted with the machine, basically. You have a part of the proof that says any map, any sufficiently large map, must contain one of these configurations, and you give an explicit list of configurations. And then for each of those configurations, you have a reducibility thing that you can color this map if and only if you can color a rather smaller one. And that, putting those two things together, you prove that there can't be a minimal counterexample that needs more than four colors. And what happened with the original proof is that they generated this list of configurations to be proved reducible by hand, and then the machine, they had a machine program that tested reducibility. Now, as soon as this came out, there was a tremendous amount of discussion in things like the Scientific American and the New Scientist, and in mathematics departments all over the place. And the discussion rather missed the point. The discussion was, can we call it a proof if the machine did it, or if it was only surveyable,
or if no human could ever check it?
Yeah, or no human can check it, and so on. Is it really a proof? The real problem was with the, let's call it the hand component, or the human component is perhaps a better word. The human component was unreliable. Even when they announced the proof, they were still finding cases that they'd missed. But what happened is, if you missed a case, you put it into the machine, and then either it proved it reducible or it didn't.
Counterexample.
But then after you, suppose it didn't, then you sort of asked, well, what are the next two faces around here like? That splits it into 3 or 4 subcases, and you put those into the machine, and the machine would check that they were all reducible. Or maybe one of them wasn't, but then you do it again, and it really is. And they had accumulated a sort of familiarity with what the machine did, and they sort of knew that they were just essentially there, if whatever case you handled, it was either reducible or could be split into a few cases, which maybe one of them needed to be split a bit more, but in any case, in the end, they were all reducible. And they made the mistake, in my view, of announcing the result when, in fact, they were still finding errors, but they were eventually cleared up. The sort of public discussion of this never centered on that. The problems were not with the machine part. The problems were with the human part. The human part turned out to be highly unreliable, as anybody with any experience of mathematical proofs could have told you, There was a man whose name I think was Allaire, Allaire, who had almost finished a proof at the time that
a similar machine-based proof.
That Haken and Appel published their proof, and he came up with his proof about within the next 6 months or so. And the original proof had about 2,000 cases to the tree, 1,900 and something. Allaire's proof was a bit smaller, And then eventually, my colleague here, Paul Seymour at Princeton, totally mechanized the proof. He mechanized the case discussion part.
So there's no human involvement?
No human interaction at all, so to speak.
Whereas mathematicians wanted to take it the other way.
Yes, I mean, by the way, I had an idea, still have, about proving the four-color theorem, but anyway, Seymour reduced it to 640-something cases. And moreover, that has been sort of hand-checked because, well, no, hand-checked, the case discussion part has been hand-checked. The reducibility was never a problem, you know. There are several different programs have been written to check reducibility, and you couldn't run it on any one of them and it says it's reducible, you know, and they're using slightly different methods. The case that I was involved in, rather reluctantly, but I wasn't really involved, was when this, perhaps I won't mention the name.
I mean, you were involved in Hales's sphere packing conjecture.
Another mathematician claimed to have a proof of the Kepler conjecture, how densely you could pack spheres. And, well, perhaps the nicest thing to say is it wasn't a proof and the claim didn't stand up. It took quite a lot of discussion to sort of verify that.
But that was not a computer proof. I mean,
no.
Computers weren't an
Now,
issue then.
Hales and his student Ferguson eventually produced a proof that the world believes. On the other hand, it started off the same kind of discussion again because it involved heavy computation. I had, I think it was a heart attack, and I was recuperating from it in Princeton. And I heard what the Annals of Mathematics was proposing to do about this Hales proof. And I was so upset by it that I telephoned the chairman of the editorial committee and suggested I come and make a presentation to try and stop them doing this.
And what were they proposing to do?
Well, what they were proposing to do, and it's what they in the end did, and I'm still upset about it, they refereed Hales's proof, well, the Hales-Ferguson proof, which should always include Ferguson, in two separate parts. One was the sort of theoretical discussion, which they sent to a team of essentially Eastern European mathematicians, referees, who had been interested working on similar problems themselves and so on. And they issued a normal referee's report. But then the computational part, they didn't quite do that with, and it was published in another place and so on. And unfortunately, the editorial comment about this sort of left a number of people with the impression that this computational part was not thoroughly checked. Well, I mean, to say it's not checked gives you the impression that it might be wrong, you know, which I think was very misleading, because what Hales did was, in my view, set a new standard for these computer-assisted proofs. You can discover, you know, you can go to their website or something, and you can ask for when this particular part of the proof was discussed, you know, and they'll say August the 12th, 1990 something, and then you can have a complete log of all the interactions between the people and the machine on that date. And it amounted to proving a certain inequality. And suppose the inequality is for two functions of one variable. F is always less than or equal to G, you know. Then you divide the interval up into a finite number of regions, and you check that the inequality holds at all the division points, and then you have bounds for the derivatives of the function. It not only holds, but it holds with something to spare, and it can't vary by more than so and so it's true on
Yeah.
each subinterval. And but then it goes further than that. They carefully use interval arithmetic, so they don't just use real number things. They
So they
use
avoid any round-off error.
real numbers with possible error marks attached to them and so on. And my God, the precautions they took were absolutely fantastic. And you can examine any particular piece of it you like. And in my view, the annals took a wrong view, which is remarkable since they're a good journal, of what the referee's job is. It's a pity because we should be celebrating the setting of a new standard for proofs by machine.
And it probably is going to become a bigger question.
Yes, I mean...
I don't know if you were involved in any computer proofs. I mean, certainly the work on large sporadic groups involved a lot of computation.
Yes.
I don't know if J4 was computer dependent.
Yes, J4 was an example. I was, in a way, involved in J4. Didn't do any programming or anything, but...
You were one of the authors of a paper.
It was a fairly big computation. However, I don't think any, in that case, or in any of the similar cases that, involve these big groups, that there is really any of this sort of supposed difficulty involving the machine.
Well, no one caused any problem in group theory.
It was clear what the machine was doing in every case, I think, and it was doing things where you could reasonably expect that it was getting them right, They were sort of... After all, suppose in a mathematical paper, somebody has occasion to refer to the product of two 5-digit numbers. And nobody feels, I have to get out my calculating machine or my thing and check that the product of these two 5-digit integers is the other one.
But was the use of a computer for either the four-color theorem or the Kepler conjecture very different from that? The machine was doing fairly straightforward calculations.
Yes, that's what I think. In all these group theoretical things, with many of them, the essential part was a coset enumeration program.
Or a multiplication of matrices.
And that's routine. And if you don't believe the answer to so-and-so's enumeration, you can do it on somebody else's program.
But you're still left with a machine doing it at the end.
Yes, you certainly are. I feel a little bit unhappy about some of those things. I suppose, since I've gone on about the monster, I'm unhappy with the computations involved there, even though, in my version of Grice's construction, and I think in Grice's original construction...
His version, he said, the computation was so large he had to do it by hand instead of by machine.
Yeah, that's right.
Was his quote.
Yes, that's true. When I've had various plans for studying the monster, and a lot of them, you will remember Len Soicher, a mutual friend, he proved a lot of things about the monster by coset enumerations, but the final things, to get to the monster itself,
was beyond.
It was too big to be done by machine. It still is, I think. The big thing there was, to find clever ways of thinking of it by hand. Grice found a way of constructing it with no use of computation, I think. There may have been some trivial use, I don't know. I simplified his construction. I read his paper to see what to do.
And he gave you a roadmap for your construction.
And then I had this idea of using... Well, Parker had the idea. Parker had this clever construction in terms of a loop, which there were two things wrong with it. First of all, he didn't feel competent to actually do it himself. And then the other thing is, he had the construction slightly wrong. You needed to do an extra twist. But, he didn't find that twist, and I did. This was on the occasion when I was sitting outside while my wife was attending the lectures. It produced a very simple construction, in my view. Yeah, well, you know, when you talk about the monster, it has a terrible effect on me. I want to start thinking about it again, you know.